Hello everyone, I'm honored to give a talk about my studies. My name is Peifeng Liang. I'm from Jiangsu University of Technology, China. Here, my presentation is about deepfake detection models. The title of my presentation is Official Geometry-Based Detection Models for Face Manipulation using CNN-LSTM architectures. My presentation consists of four parts. First part is introduction. Second part is propose the CNN-LSTM architecture. Third part is experiments, and at last is conclusions. At present, deep learning, computer vision, and other technology related to computer sciences have made great progress and benefiting from the development of technologies. A very interesting technique called deepfake has attached the great attention. By means of deepfake technologies, everyone can generate a lifelike face in the videos or imagine that doesn't exist in real world, or implement facial manipulations, as shown in these PPTs. Although deepfake has brought us fans and promoted the development of science and technologies, it will also bring us great design if it is not applied properly. For example, the abuse of deepfakes has penetrated every corner of social media, and the deepfakes may cause great threat to privacy, democracy, and national security. Therefore, deepfake detection has been a very hot issue in deep learning research. So our motivation in this study is to propose a deepfake detection model for fake face images. Our proposal model can identify manipulated images or locate the manipulated regions. The contributions of our studies is as follows. A novel fake face detection framework is proposed that explores the localization of a manipulated region by using feature maps in the frequency domains and facial geometric context. Secondly, different from most of the existing studies, our studies explore the utilization of facial features in manipulated face detection for the first time. At last, we highlight the research challenges that impede the adoption of deepfakes in multimedia applications. Our study work aimed to detect the manipulation in the face images and identify the real face or not. So, our proposed model is composed of three parts. First part is the CNN-LSTM network. Second part is the FGPM model. Here, the FGPM means facial geometry prior models. And third part is decoder and classifier networks. The CNN-LSTM network can learn the boundary of a transaction between non-manipulations and manipulations in the frequency domains. The FGPM models combine the feature maps for LSTM network with facial geometric maps of social images, like facial landmarks, which allows our proposed approaches to achieve good localization capabilities. The decode provides representations of manipulated regions in the mask, so we can easily locate the fixed region of face images. These figures show the models in our studies. As we see, it consists of three parts. The first part is LSTM networks, and the second part is facial geometric prime models, and the third part is a decoder and classifier. Let's see the first part, LSTM network. The input of LSTM is resembling features of pitches. So in this part, we first divide the image into many pitches. Each pitch is a size of 16 multi-16. And in second step, we need to extract the resemble features. And then we input the resemble features into LSTM networks. So the size of a LSTM network in our proposed models is 4 static layer and 44 times depth, as shown in these figures. The facial geometric prime model is very important in our proposed model. It can provide the key features of face landmarks, as shown in these figures. This figure shows the input and output of FGPM models. In these models, there are 3 input feature maps. The first is a feature map for detection resembling, which is the output of a CNN-LSTM network. And the second feature map is a feature map with facial or landmarks. This feature can be extracted by using CNN networks. And the third feature map is facial geometric maps. It is very important in our proposal models. So in our models, we propose a network which extracts the facial geometry maps. The network is shown in these figures. This is the input margin, and it is input into encoders, as shown in this figure, and this is a decoder, and at last it outputs the facial geometric maps. In this architecture, we embed a teaching model. It's shown in this here, and here. It is very important. At last, we need to introduce the decoder and classifier. The decoder is used to decode the feature information output from FGPM to locate the manipulated readings, as shown this here. And a classifier is utilized to predict the pixel-wise classification at the end of the decoder network, or predict fake or real face images, as shown this. So in this part, you will input the feature into a decoder. We can locate the manipulated regions. Or you will input the features into a classifier. We can identify the feature is a face feature, is a face or not. The second part of my presentation is an experiment. In this experiment, we use 5 data sets. They are CLAs, face fluency, deep fluency, and Google deepfake detections. At the same time, we select 4 methods as baselines to compare with our proposed approaches. And this this table shows the simulation result of our proposed models and other detection approaches. For this table, we can see our proposed model achieve better performance, which is shown in the result of F-score and recall and accuracy. Let's see that our proposed method achieve a higher F-score. And we also show the fingers of AUC circle. For the finger, we can see our proposed method achieve the best result of AUC. Let's see this and this and this and this. At last, we also show the result of segmentation detection. The left fingers is a result of real face. This means our proposed method locates the manipulated regions of real images. For this finger, we can see there are almost no manipulation regions in the master images. And right finger shows the result of fixed images. we can see our proposal our proposal process shows the manipulate regions like this, and like this. It is very accuracy. And this demonstrates that our proposal approaches is at last is our conclusions. In these studies, a deep learning-based approach is proposed that can identify the face manipulation by taking advantage of CNN-LSTM models and visual geometry features. In these approaches, a special CNN-LSTM architecture is developed that effectively discriminates real and fake regions in the face images. We explored a facial geometry prior model that provides facial geometry feature maps of manipulated objects. Finally, to predict the manipulation localizations, we design a decoder that learns the mapping from low solution feature maps to pixel-wise, or a softmax classifier is used to predict the real or fake or fake face images. The proposed deepfake detection model is experimented with some datasets and achieve outstanding performance. This is my presentation. Thank you for your attention.